hello everybody. Welcome. Welcome to our first round of lightning talk of the semester. And we are very happy to have our 4 speakers here, and each of them will have 5 minutes. Okay, let's start. Our first one is Donna. Let's welcome Donna.
Oh, no.
I'm so sorry.
It's JP, right?
It's
Yeah, we didn't permute identity.
Very sorry.
That's okay, no problem. All good?
Yeah.
All right, thanks so much for having me. And again, I'm JP for the record, not Donna in case. So I wanted to talk about digital phenotyping, which is one of the 2 research areas in my lab, the other one being statistical network science. So what's the scientific problem that we're trying to solve? So this is a problem that's often called the phenotyping challenge. So I want to say a couple of words about this. So first, briefly, phenome is a complete phenotypic description of a species, including anatomy, transcription, enzyme activity, and behavior, among many others. And of course, analysis of phenotype plays a huge role in clinical practice and medical research, but our definitions and descriptions of phenotypes are surprisingly imprecise. And that's why many investigators for the past 20 years have been propagating the greater role for phenotyping in the biomedical sciences. And this is usually done for 2 different reasons. One is for analysis of phenomic data per se, and the second reason is for joint analysis of phenotype and genotype data. Behavior has traditionally been a very difficult phenotype to study for 2 reasons. One is behavior is time dependent, and behavior is also context dependent. And we're especially interested in behavior in psychiatric and neurological studies, where we currently usually rely on surveys to get this type of information. So what we think we need is a scalable way to measure social and behavioral markers out there in the wild as people live and experience their lives. And the proposed technology that we're using is the same technology that's being used to time this talk, which is the smartphone. And the reason we're using this approach is because these devices are very sophisticated technologically, and their numbers are incredible. So this is the fastest spreading technology in the history of people. So in 2015, there were 3.2 billion smartphone subscriptions in the world. By 2021, 6.3 billion are expected. So these are very large numbers. So what do we actually mean by digital phenotyping? We've defined digital phenotyping as the moment-by-moment quantification of the individual level human phenotype in situ, in the wild, using data from personal digital devices, in particular smartphones. And we think that this approach has 3 distinct advantages compared to other approaches to phenotyping. One of them is that we can have large-scale studies, so maybe tens or hundreds of thousands of individuals. The second benefit is that because we try to rely almost exclusively on passive data, things like sensory data from the phone, we can have very long-term studies without adherence issues. And the third benefit is really a combination of the first 2, which is that given these 2 points, we can do population-level studies where we have not only the post-data, data after, say, somebody develops PTSD symptoms, but also the pre-data, what happened before the onset of those symptoms. So we started this project about 5 years ago, and we had 3 distinct goals. Our first goal was to develop infrastructure for collecting these types of data using smartphones. Our second goal was to build methods. The data are big, but they're primarily noisy. We get about 1 billion data points per subject per month, so we somehow have to try to make sense of these data. And the third point was we wanted to run maybe 1 or 2 studies at different HMS hospitals, but as it turns out, I think we have 14 or 15 studies now, so this thing kind of exploded. So our overall goal in this area is to systematize data collection and data analysis in smartphone-based digital phenotyping. I'm worried about hearing some kind of a weird sound soon, so let me pick up the pace. So as part of our work in this area, we've developed what we call the BV Research Platform. So this is based on the AWS cloud. It's open source, and we think it's pretty cool. So if you're interested, you can take a look at that. We've tried to tackle several interesting statistical problems along the way. So just to give you a flavor, one of the problems is with GPS data, we typically have a lot of missingness. So the question is, how should we impute the missing data? Another interesting problem is, how can we estimate the onset and offset of sleep using various types of data from the smartphone, like gyroscope data, accelerometer data, and so on. A third very interesting example is, how can we detect behavioral anomalies? For example, in our schizophrenia study, it's very common for individuals to relapse, and then they require hospitalization. So is there a way that we can somehow combine these data streams to do that? So just to give you a 22-second flavor of an actual ongoing study, this is at the Brigham. This involves patients with spine disease. This is a person in the study before surgery. This is the same person after surgery. Can I repeat one sentence? The question is, does this work? So we have 22 weeks of data here. Every day we ask, this is the surgery, we ask what happens to a person's pain level, but we also have the passive data measures that tell us a lot about the actual functioning of that person. So thanks for using a great sound. Thank you.
I think we have a few minutes for questions for GP. So anyone have questions? Donna, please.
Hi, so on the subject of digital phenotyping, is there any kind of validation studies that are being conducted where the digital phenotyping is being compared to, say, for schizophrenia, a physician-based diagnosis and so forth?
Yeah, so essentially in all of our studies, sorry, I'm trying to see you, but I think so yes, in almost our studies. So one example is our sleep study, where we use an FDA-approved wearable in our subjects, and that's really the best way to learn about sleep in situ. If you wanted to get better data on sleep, you can go to a sleep clinic. But the problem that you have then is that you have a very artificial setting. So we have this photo or picture of a 5-year-old boy who is at a sleep clinic, and he has like 200 wires connected to his head. So we're getting great data, but it's a completely artificial setting. So we absolutely try to do external validation for all of these things. All of our studies involve clinicians as well. Yeah, absolutely. And I didn't do the surgery here. This was done by my research colleague. Yeah. Any other questions? Oh, sorry, you're the
Any other questions?
How do you get missingness in the GPS data? Is it just kind of what you would think it would be when your watch loses connection?
So this is a great question. Why is there missingness? So short answer is, if you turn the GPS on your phone, it's going to kill the battery in about an hour. So the problem is you cannot sample it continuously. You have to cycle between on and off cycles. So you collect it maybe for a minute, and then you don't collect it for 10 minutes. So this gets around the battery problem. But the challenge with that, you might think that why don't we just turn it on for 1 second and have it sleep for 10 or 15 seconds? But it has to find the satellites, especially if you're in an urban setting. You only see a small piece of the sky, so the spatial angle is very small. So typically you need 30 to 45 seconds to find the satellites. So the missingness is there by design, usually by design, to avoid battery drainage. But that's not the only kind of missingness. Yeah. Does it make sense?
Yeah.
Okay, let's send GP again.
Thank you.
Okay, our next speaker is Kyler.
Okay, so I will be speaking on a new metric for sensitivity analysis for unmeasured confounding, which I'm calling the E-value. In my view, in pretty much any observational study intended to assess causality, we should be assessing sensitivity to unmeasured confounding, and yet this is still rarely done today. And so this is an attempt to provide a method that is both rigorous and easy to use. So the setting that we're in is we have some exposure or treatment and observational data. We want the effect of that exposure treatment A on our outcome Y. We've adjusted for a bunch of measured covariates C, but we're worried that some unmeasured factor we don't have data on affects both the exposure and our outcome. And we want to assess how strong do those effects have to be of the unmeasured confounder on the exposure and outcome to explain away our effect. What we do and what many methods do is it compares our estimate of, say, the risk ratio of, for the effect of the exposure on the outcome conditional on measured covariance C to what we would have obtained as an adjusted risk ratio if we had been able to adjust for U as well. And the ratio of those two, our estimate adjusted for C and the truth, had we been able to control for U, we define as the bias factor. Most sensitivity analysis techniques then express that bias factor in terms of parameters that relate the unmeasured confounder to the exposure and the unmeasured confounder to the outcome. There are many, many such techniques, but these techniques are often criticized because they make assumptions. Often they assume a binary unmeasured confounder. Sometimes they assume that there's no interaction between the unmeasured confounder and the exposure and their effects on the outcome. Most of the techniques assume that there's only one unmeasured confounder. And so these techniques are sometimes criticized for making assumptions to assess assumptions. And then what do we really gain? So this is an attempt to relax these various assumptions. We're going to define two parameters. The first parameter, our UY, is essentially the maximum risk ratio relating U and Y. We compare any two categories of U amongst the unexposed, look at their effects on the probability of the outcome Y. We take the maximum such risk ratio. We do the same thing for the exposed subjects. What's the maximum effect relating U and Y amongst the exposed subjects? And then we take the maximum of those two. That's our first parameter, essentially the maximum risk ratio relating U and Y. Our second parameter, RRAU, is the maximum risk ratio relating exposure A to any particular category of U. It turns out, with parameters thus defined, the maximum the bias factor can be is just the product of those two parameters divided by their sum minus 1. We can then take our estimate confidence interval, divide it by this bias factor to get an adjusted estimate and confidence interval. And this is the most such an unmeasured confounder could shift our estimates. This bound is also sharp insofar as it's always possible to construct an unmeasured confounder that obtained those bounds. So what is the E-value? The E-value is the minimum strength of association on a risk ratio scale that an unmeasured confounder would have to have with both the exposure and the outcome conditional on the measured covariance to explain away the exposure-outcome association. Using that bias factor, we can derive the E-value, and it takes a very simple form. The risk ratio plus the square root of the risk ratio times the risk ratio minus 1. If the initial risk ratio is protective, we first take inverses and then apply the formula. The proposal is to always report this E-value for both our estimate and the limit of the confidence interval closest to the null to assess how sensitive our estimates are to unmeasured confounding. As an example, here are 3 estimates from various studies looking at the effect of breastfeeding on different child and maternal health outcomes, including respiratory tract infection, maternal ovarian cancer, childhood leukemia. If we took, say, respiratory tract infection, risk ratio 0.8, confidence interval 0.14 to 0.54, we take the inverse of 0.28, plug it in the formula here, we get an E-value for the estimate of 6.6, E-value for the upper confidence interval of 3.1. That would mean to explain away the effect, to shift the confidence interval to include the null, it would have to, an unmeasured confounder would have to affect both breastfeeding and increase the risk of low respiratory tract infection by 3-fold each, above and beyond the measured covariance, to explain this away. So pretty strong confounding would be needed here. We would think our estimate here is pretty robust to unmeasured confounding. But if we move to some of the other outcomes, we see the E-values are somewhat lower. We perhaps still have moderate evidence for an effect on maternal ovarian cancer subsequently, but much more modest evidence for childhood leukemia. So that's the notion of the E-value. We've done this for other effect scales as well. We have an E-value, online E-value calculator, as well as our package produced by Maya Mather here in this department. You can download the paper in the Annals of Internal Medicine published last year, as well as the R package and the online calculator from my website under Tools and Tutorials. Thank you.
Any questions for Taylor?
That's great talk. So what cutoff would you recommend people to use for the E-value?
Yeah, so that's a good question. I mean, I try not to draw a line in the sand. I feel so much mischief has been done by the p-value 0.05 cutoff that I'm very hesitant to suggest something. It is also context dependent, what's a large and small e-value. So if our outcome were all-cause mortality, an e-value of 2 would be really quite substantial. We don't have all that many risk factors that increase mortality or decrease mortality by 2-fold. But if it were something like suicide, where we have risk factors that increase the likelihood by 3-fold, 5-fold, 10-fold, an e-value of 2 might not be all that large. But I think if you go through the epidemiologic literature, we often see risk ratios of 1.2, 1.3. So those risk ratios wouldn't necessarily indicate all that much robustness. Once we get to an e-value of something like 1.5, we observe effect sizes of that magnitude much less frequently, and it would have to affect both the exposure and the outcome by a risk ratio of 1.5, if we had an e-value of 1.5, to explain away the effect. So I think an e-value of 1.5 for the confidence interval provides reasonably strong evidence, but again, it is context specific.
Okay, thank you for the question, and thanks so much. Now it's time for our third speaker, Donna.
Okay, so I'm going to talk about opportunities in biostatistics for implementation science. And implementation science is a somewhat new area, and an area that I'm going to first explain. So here's a cartoon that kind of illustrates the issue that we're addressing in implementation science. The latest research shows that we really should do something with all this research. So here we have a flow chart of the publication pathway, and the bottom line here is that it takes 17 years to turn 14% of original research to the benefit of patient care. So the idea in implementation science is to try to speed up this pipeline so that it's much less than 17 years, and identify the barriers to translation of the other 86% of research so that we can move on to using all the knowledge that we've generated in public health, say, over the past 50 years, which is quite substantial, to improve public health, both here in the United States as well as globally. So you might wonder about a definition of implementation science as an evolving field. It's got evolving definitions, and these are 3, but maybe this is the simplest one and one that I like a lot. It's very comprehensive. Implementation science is about determining what works in real-life, full-scale settings. So that's what we're doing, and some of you might know I've had this NIH Director Pioneer Award for the past 3.5 years. I've got several years to go, and its focus is to develop and consolidate statistical methods aimed at implementation science applications. So I'm going to go through a few of these right now, just to give you a feel, and a number of people in the department have been involved in this work over the past 2.5 years. So here, this is a former postdoc of mine who also got a master's degree here and worked at CBAR, Ashley Buchanan. She's now an assistant professor at the University of Rhode Island. And we worked on causal inference for estimating individual and disseminated effects in network interventions, and specifically in HIV prevention. And the idea is here that through the network, you can randomized network study, you can estimate the causal effect on the networks, but then within the networks you have index participants and participants who are only involved insofar as they're socially connected to the network members, and there can be indirect effects on those individuals. Once you get into the weeds of the network structure, you're no longer in a randomized study setting, and we have to use observational methods for causal inference to estimate these separate effects. So here, this is another colleague of mine, Mo-Lin Wang and Polina Kudyakov, and this project here, we're developing empirical methods for estimation and inference for the incremental cost-effectiveness ratio using modern semi-parametric survival data methods. Now, I can say here to this group that biostatistics has kind of dropped the ball, as well as epidemiology, in providing quantitative methods for the kinds of projects that I'm talking about here. And who's jumped in are the health economists. and they're actually leading most of the quantitative methods development right now. And they often don't have the kind of background that we have in biostatistics. For example, to estimate the incremental cost-effectiveness ratio, you need to estimate the mean survival time or the median survival time, which is interesting in itself because in biostatistics we've mostly focused on the hazard ratio in survival data analysis. And now for the first time I'm actually thinking about these absolute measures. And there's very different issues in terms of the absolute measures in terms of confounding, external generalizability, and so forth. So not to think that this is the actual structure of the formula in a very simple case. And these equations are just to give you an idea that to solve some of these problems, we have to get into some of the deepest and most theoretical aspects of different kinds of statistical inference, and in this case, survival data analysis. Sometimes people think if you're dealing with a very practical problem, it means that you'll be using sort of a simple 2x2 table. But in fact, the more complicated and messy and large the data are, in my experience, the more challenging the statistical problems are, rather than the less. Now here, some of you might know Lauren Coons. She graduated, I think, about 2 years ago from the department. I think she's now working at the analysis group after having gone to NHLBI as a staff statistician there and a former research scientist of mine. And here, we're working on methods and software tools for step wedge designs. So this is a design, this is the sort of graphical structure of the, oh my God, okay. So I'm going to show you, there's lots of other projects underway. The green are open areas, either that would be brand new or new developments from things that have already been somewhat worked on in colleagues of my group, and there's a bunch of these here, and then some new areas that we haven't worked on at all, and then, oh, this was supposed to, I said, who said statistics isn't fun? Because in fact, there's tremendous interest in this work all around the world. I just recently returned from a trip to India, Nepal, Tanzania, and at the Indian International Statistical Association, where I was the keynote speaker. This is supposed to, I don't know if you can click it, it's supposed to show the, it's supposed to, this one, yeah. Oh, yeah, so just click it on. So I thought while I was answering questions, I can show you the amazing performance of Kuchipudi fusion dance that was given at the International Indian Statistical Association. I guess the sound isn't on, though.
Oh.
Because it's really nice music also. So while we're watching, oh, here we go. So while we're enjoying this great performance, I can take a few questions. Yes?
I'm just curious, the flow chart you showed at the beginning of the path from science to actual benefits for people, where do you think is the biggest bottleneck in terms of the speed and efficiency of that kind of thing?
Well, you know, it's from what I remember, I mean, we could go back to it, but I think it's kind of incremental. Like each one of these adds on a few years, and then it adds up to the 17 from one step to the next, starting from getting funding, doing the project, getting the project completed, getting it published. Things get shunted off because of, say, publication bias, then sitting around in the literature, then being picked up in some kind of review, then the reviews being used maybe later on to translate to policy, and all of those different steps, as well as some that I forgot, start to add up to 17 years.
Okay, thank you so much. At this moment, we need to turn off the Facebook live stream. Welcome to